A frost-covered power line hums against the pale gray light of a damp suburban dawn. Perched above the sleeping cul-de-sac, a New Caledonian crow adjusts its grip on the cold, galvanized steel. Its obsidian feathers absorb the dim light, practically invisible except for the sharp, calculated tilt of its head. The bird is not scanning for insects or fleeing a predator. Its dark lateral eyes are fixed on a specific human walking down the driveway below, carrying a yellow recycling bin. The crow tracks the human's stride, measuring the precise interval of the footsteps against the pavement. It knows the schedule. It understands the routine. Above all, it recognizes the face. For decades, classical ethology operated under a comfortable hierarchy. Primates sat at the apex of non-human intelligence, celebrated for their hand-eye coordination, complex social structures, and ability to modify sticks to fish for termites in the African savanna. Birds were dismissed as hardwired biological automata, driven strictly by instinctive loops governed by a rudimentary basal ganglia. The term bird brain was a settled scientific insult. Yet high in the canopy and along the power lines of our modern cities, a quiet, cognitive revolution has rendered that classical hierarchy obsolete. Consider the physical mechanics of a tool. To shape an object, an animal must possess a mental blueprint of a future state, a concept that does not yet exist in the physical present. In the humid forests of New Caledonia, wild crows routinely locate the stiff, barbed leaves of the pandanus tree. A crow does not merely grab a twig and poke blindly into the bark. It steps deliberately along the leaf margin, making a series of precise, angled snips with the sharp edge of its beak. It rips a tapered strip of leaf, wide at the base for a firm grip, narrow at the tip, and lined with natural, backward-facing barbs. This is not accidental tearing. It is a standardized, multi-step manufacturing process carried out without hands, thumbs, or a prefrontal cortex. To truly understand the depth of this anomaly, one must examine the neurological architecture involved. Mammalian intelligence relies heavily on the layered cerebral cortex, particularly the prefrontal regions responsible for executive function, planning, and abstract reasoning. Avian brains lack this layered cortex entirely. For over a century, neuroanatomists assumed that without these mammalian layers, complex thought was impossible. But recent microstructural imaging reveals that corvids have organized their forebrains into dense, highly interconnected clusters of neurons known as the nidapallium griseum. These avian neural clusters pack neurons at densities far exceeding those found in chimpanzees or baboons. The crow does not lack an executive center. It simply built one using a completely different evolutionary blueprint, packing millions of signal processing nodes into a space no larger than a walnut. When a laboratory experiment presents a crow with a complex physical puzzle, the bird does not engage in trial and error bashing. Place a deep, clear acrylic tube containing a small basket of meat in front of a captive crow and lay 2 pieces of wire on the table beside it, one straight, one pre-bent into a hook. The crow will immediately select the hooked wire to hoist the basket out, but alter the experiment. Present the bird with only a straight piece of flexible wire. The crow will hold one end of the wire down with its heavy, scaly foot, grasp the opposite end with its beak, and bend the metal against a hard edge until it creates a functional hook. It solves a novel physical problem on the very first attempt, demonstrating an internal, spatial simulation of physics before it ever moves a single muscle. This capacity for sequential planning reveals a profound leap in animal cognition. In controlled behavioral assays, scientists designed a 7-step puzzle that required an animal to use a short stick to retrieve a longer stick from a locked box, and then use that second, longer tool to reach a piece of food hidden deep within a narrow crevice. To complete the sequence, the subject must restrain its immediate impulse to reach for the food, turn its back on the reward, and execute a series of intermediate, abstract goals. Chimpanzees struggle with this level of delayed gratification when multiple tools are involved. The crow, however, approaches the 7-step matrix with calm, eerie efficiency. It pauses, stares at the apparatus for several seconds, as if running an internal computer simulation, and then executes the sequence without a single hesitation or incorrect move. The implications of this spatial logic shatter our traditional understanding of cognitive evolution. A creature with no hands, no opposable thumbs, and an evolutionary trajectory that diverged from mammals over 300 million years ago has arrived at the exact same functional problem-solving capabilities as the highest primates. The crow looks at a raw, unformed world of wires, branches, and trash, and sees not what those objects are, but what they could become. In the quiet, damp light of the suburban morning, the crow on the power line drops its head, lets out a low, guttural click from deep within its throat, and swoops silently toward the ground. It is not searching for a free meal. It is deploying a tool it modified 10 minutes ago, tailored specifically to the exact dimensions of the drainage grate beside the curb. The observer on the sidewalk sees only a black bird poking at the gutter. The neuroscientist sees a master technician at work, operating a mental engine that rivals our own. A rubber mask featuring a distorted human face rests on a wooden bench inside a quiet university courtyard. To a human passerby, it is a grotesque novelty item. To the flock of American crows circling high above the manicured oak canopy, that synthetic face represents a persistent threat registered across multiple generations. In a landmark study conducted at the University of Washington, researchers wearing specific latex masks captured and banded wild crows before releasing them back into the park. Years later, long after the original birds had died, masked researchers walking across the lawn were met with deafening mobbing calls. Birds that had never been handled by human hands descended from the branches, diving with outstretched talons toward the single synthetic face. This behavioral anomaly reveals an extraordinary cognitive mechanism: the ability to form abstract, highly specific facial profiles and transmit that intelligence culturally across vast social networks. Corvids do not merely recognize individual human faces. They encode the structural spatial ratios of eyes, nose, and jaw into long-term visual memory. When a crow identifies an enemy, it utters a harsh, pulsed alarm call, a rhythmic vocalization featuring subtle shifts in acoustic frequency that convey the exact nature and location of the threat to surrounding birds. Young fledglings listening from the nest absorb this vocal data, internalizing a specific human face as a target of collective hostility without ever having experienced a direct encounter. This transmission of knowledge demands a complex form of mental time travel. For decades, cognitive psychologists argued that episodic memory, the capacity to re-experience past personal events and project future scenarios, was uniquely human. We assumed animals lived in a perpetual present, driven entirely by current physical drives. Yet cache-hiding behaviors among scrub jays and crows dismantle this assumption completely. A crow hiding a surplus meal of raw meat or shiny metal trinkets beneath a pile of damp oak leaves performs a complex series of tactical calculations. It considers who is watching. If another crow is perched on a nearby fence post within visual range, the hiding bird will pretend to bury the item, quickly slip it into its throat pouch, and fly to a secluded spot behind a rusted brick wall to complete the true cache. Even more striking is the bird's ability to calculate the decay rate of its hidden assets. In controlled field trials, crows cache two types of food: perishable waxworms and non-perishable pine nuts. When allowed to recover the food after a short interval of 4 hours, the birds consistently dug up the perishable worms first, maximizing their nutritional gain. But when the recovery period was delayed by 3 days, the crows entirely bypassed the rotting worms and went straight for the preserved pine nuts. The bird's internal clock does not merely count elapsed time, it projects the future physical degradation of organic matter within a specific spatial coordinate. It replays past caching events frame by frame, recalling precisely what was buried, where it was placed, and who was watching when the earth was packed down. This level of social attribution requires what neuroscientists call theory of mind, the ability to attribute mental states, intentions, and knowledge to other individuals. A crow only engages in deceptive caching tactics if it understands that the observing bird possesses its own visual perspective and intent to steal. To deceive another creature, you must first construct a mental model of that creature's internal world. You must recognize that their eyes see what your eyes see, and that their actions will be driven by the information they gather. When a crow misdirects a competitor toward an empty patch of grass while concealing a stolen bone under its wing, it is executing an active campaign of psychological warfare. As urban environments expand, replacing dense pine forests with concrete canyons and tangled electrical grids, corvids are not merely surviving, they are rewriting the rules of urban ecology. In busy intersections across Tokyo, Japanese carrion crows use moving automobile tires as heavy mechanical nutcrackers. The bird drops a hard walnut onto the cracked crosswalk asphalt, then hovers safely on a traffic light housing, waiting for a vehicle to roll over the shell. But the bird does not risk its life diving into active traffic. It waits for the illuminated red light to stop the stream of steel cars, walking calmly onto the crosswalk alongside human pedestrians to retrieve the exposed kernel. It leverages human infrastructure, traffic signaling systems, and mechanical mass to achieve an objective that its own beak could never accomplish alone. Comparing this fluid adaptability to primate intelligence exposes a fascinating evolutionary paradox. Great apes possess massive brains relative to their body size, opposable thumbs, and millions of years of evolutionary history within stable, resource-rich jungle environments. Yet when placed in novel, fast-shifting urban landscapes, primates often struggle to adapt their hardwired social structures and foraging habits. Crows with a brain the size of a single walnut navigate our complex cities with breathtaking agility. They decipher human schedules, operate heavy physical machinery by proxy, manufacture multi-component tools out of discarded industrial trash, and pass complex cultural knowledge down through generations without a written language. The ancient divide between bird and mammal was never a measurement of raw mental capacity, but a divergence in architectural engineering. While mammals built massive, energy-intensive brains wrapped in thick cortical layers, avian evolution compressed neural wiring down to its absolute limits, optimizing processing speed, signal density, and spatial flexibility. The crow perched on the street lamp does not view the city as an alien concrete wasteland. It views the city as a vast, interactive laboratory of physical mechanics and human behavioral patterns. When you look up at a glossy black silhouette resting against the twilight sky, you are not looking at a primitive survivor of the dinosaur era. You are looking at a parallel intelligence, a cold, calculating technician that has analyzed your face, mapped your habits, and mastered the logic of the toolmaker using nothing more than a curved beak, a cluster of hyper-dense neurons, and a mind that sees 5 steps into the future.